I'll start. So tonight we have got Professor David Waltham on Is Earth Special, just a couple of minutes away. So let's just go through the normal. Next slide, please, Mark. For any visitors following us on YouTube, you can find out all about the Astronomical Society of Edinburgh on our website. And you'll also find links to the YouTube channel where you can follow any of the talks we've had during lockdown at your leisure. Tonight, if you have any questions and you're using YouTube, if you put them in the comments section, we'll try and pick them up. For members joining by Zoom, it's the usual, put them on the chat line and Peter will call them out of it later. Next slide, please, Mark. Okay, and just to remind everybody, next Wednesday, we have Dr. NonRocky, the Mission Senior Scientific Officer, joining us from Maryland, Johns Hopkins University, to talk about the Parker Solar Probe. Then on Friday, Mark is going to do part 5 on our intro to astroimaging, and it's imaging for science projects, of which there are a few, and I know some people have already started to get involved. The last meeting, we'll call it, of this term, before we have our August break, and go away and decide what format the meetings take from then on and the frequency, will be on the 31st of July. There will be a Sky in August and a bit of a catch up about what we've been doing, and a chat, I suppose, amongst members. So that's what's coming up. If anybody is still interested in giving a scope talk, I'd really be interested in hearing from you, because we can look forward to finding a slot for those soon. So, David, are you back?
Yes, I'm back, and I've got my slides set up, and I've got my cup of tea.
You share your slides when you're ready, and it's over to you.
Okay, let's hang on a minute. I need to start this one first. And hang on a minute. Too many screens on at once. Let's try. And I can't see the right screen. I've got all the screens to share except the one I want to share. Let's try that one more time. Ah, there it is now. That's it. Right. Have we got my slide up?
Not yet.
No?
No.
Oh, hang on. No.
Have you shared screen?
Is it there now?
Yes, we have.
Great. All right, so you just have a single slide, my very first slide, yeah?
Correct.
Right, okay, good. Right. So I'm going to talk about whether or not the Earth is special for about 40 minutes. And the question I'm really asking is whether what you see before you is the actual Earth any weirder than that, or as weird as that, is what I'm trying to ask. Oh, hang on a minute. Sorry, another technical problem. Okay, is the slide still there?
Yes.
Yeah. Okay. Right. So let me just go straight to the next slide. We'll take it from there. I'm starting with this this picture, which is probably quite familiar to many of you. It's a Hubble Deep Space Telescope image an 11-day exposure, and you can get a feel for the size of slice of sky we're looking at there. If you take your finger and thumb and put them about a millimetre apart, and then hold that out at arm's length, and think about the size of that patch of sky that you're looking at, if you sort of hold it up a bit, imagine that your fingers at the top of the picture you can see and your thumbs at the bottom. That's the sort of size of slice of sky you can see. And in this particular picture, we're looking at 10,000 galaxies, and each of those galaxies contains about 100 billion stars. So you're looking at quite literally a quadrillion stars in this single image. And if you were to imagine that density of galaxies across the entire sky, you're looking at 100 billion galaxies, each with 100 billion stars. You know, that's such an enormous number. We don't have a name for it. It's 1 followed by 22 zeros. So that's the number of stars in the universe. Now, I don't know about you, but I have great difficulty visualizing a number that big. But let me try to find something else that's the same size. So I'm going to start with this pint of sand. Right, so this is not builder's sand. This is not the normal sort of sand that you probably come across. We actually use this sand at Royal Holloway for modeling how rocks deform. It's very, very fine. The individual grains here are so small that you have trouble seeing them with your naked eye. You really need a magnifying glass to see them. But because they're that small, I can get an awful lot of them into a pint. In fact, there's about 1 billion of them in this pint. Now, what I want you to try and think about is how much of this sand would I need to have the same amount of sand as there are stars in the visible universe? And the answer may surprise you. You'd need a cubic mile of sand. You need a box that's a mile long, a mile deep, and a mile high of this sand that's so fine that you can barely see the individual grains. So that's the same number as there are stars in the visible universe. How are you doing? Personally, I'm struggling, and we're not finished yet. Even a cubic mile of sand is not enough, because so far I've only been talking about the visible universe. That small fraction of the cosmos that we can actually detect from Earth. Now, we can only see 14 billion light years into the universe because light from objects further away has not yet had time to get to us. However, that cosmic horizon is actually very like the horizon on Earth. The Earth doesn't stop at the horizon, and neither does the universe. Now, if the majority view of cosmologists is right about how the universe formed, and I'm talking here about the inflationary ideas about how the universe came into existence. If they're right about that, one of the implications is that the actual size of our universe, our part of that inflationary universe, is probably at least 1 billion times bigger than the bit we can see. And it may even be infinite in extent. So let's just go with a universe that's 1 billion times bigger. And to get that many sand grains as there are stars in that universe, we need a whole moon's worth of this very fine sand. So that's a big universe with a lot of stars and a lot of planets. And because it's become clear over the last 25 years that perhaps most stars have at least a few planets. And so the universe probably contains more planets than it does stars. So where I'm going with this, you can probably guess. Simple statement that surely with this astronomical number of worlds, the universe must be teeming with life. Actually, no. I think that's completely the wrong conclusion. The only thing this unimaginably enormous quantity of planets tells us is that even the very oddest of worlds will turn up sometimes. Let me try and imagine something ridiculous, yet still physically possible. Imagine a 22-carat gold planet, and imagine that it has rings, like the rings of Saturn, but made of diamond dust rather than ice particles. So this picture illustrates the kind of thing I have in mind, although a planet like this definitely does not exist anywhere in the universe because those inclined rings are not physically plausible. But imagine we've only got one ring to worry about. Is a diamond and gold planet really so absurd that it does not exist anywhere in a universe as big as ours? My guess is that it probably does somewhere. So let's try something else. Imagine a world where tiny bags of chemicals have developed the ability to copy themselves, and where colonies of trillions of such systems move together as one in search of food. And imagine that some of these colonies stare at the stars and wonder if they are alone. Well, that's Earth. And she may be even more absurd and unlikely than a planet-sized engagement ring. There are lots of things that could make living worlds as peculiar and improbable as I'm suggesting. We still don't understand how life started, so maybe it needs very special conditions, a planet of just the right size, with just the right temperature, just the right amount of water, just the right atmosphere, and goodness knows what else. Furthermore, perhaps the origin of life is an inherently unlikely accident that hardly ever happens, even when conditions are perfect. Even once started, life might frequently die out or become stuck in a rut. There really isn't much I can say about whether life arises easily on all suitable planets or instead is a very unlikely chance event, even when conditions are perfect. We simply don't know. But I can speculate about whether any of Earth's properties seem peculiar. Peculiar in two particular ways. Are any of Earth's properties peculiarly suitable for life or peculiarly rare? So here's a list of the Earth properties that I'm going to look at. I'm going to start with our sun rather than the Earth herself. Now, we're often told that our star is pretty typical. Is it? In particular, is its size typical? I'm sure many of you are used to thinking of the sun as a rather small and dim star, a star outshone by almost every star we can see with our eyes. This is true, but it's only half the story. The problem is that necessarily the stars we see most easily are the big bright ones. Most stars are actually too small and faint to be seen without powerful telescopes, even when they are close. For example, our very closest neighbour, Proxima Centauri, is only just visible in a 10-inch telescope. When you take all those dim red dwarfs into account, it turns out that our sun is actually unusually large. This graph shows how star frequency falls with increasing star mass. The numbers on the left here are relative to the sun. So you can see, for example, at 0.2 star masses, so 0.2, 1/5 of the sun's mass, hopefully you can see that we're on those graphs, we're up at around about 10 on the y-axis. In other words, stars that are 1/5 the size of the sun are actually 10 times more common. So this graph shows that stars as large as or bigger than our sun are rare. We're actually in the top 15% or so when it comes to star mass. In other words, 85% of all stars are smaller than the sun. Now, this is very surprising. Small stars last much longer than large ones. And so if you were to pick a random moment on a planet orbiting a star, so imagine you just, you had a TARDIS or something and you just completely at random went to some moment, someplace in space and time and landed on some planet orbiting some star. If you did that, you'd be far more likely to pick a planet orbiting a small star. There are more of them and they have more moments because they last longer. And life on Earth you can think of as we've all kind of randomly picked a moment on a planet. Why have we picked a random moment on a planet orbiting an unusually large and short-lived star? The implication is that there's something wrong with red dwarfs as the home stars for complex life, some reason why they're not great places to live, and hence some reason why we find ourselves orbiting an unusually large and short-lived star. There have been many suggestions about what the problem could be with small stars. For example, they tend to have more flares. Planets orbiting them within their habitable zones tend to get tidally locked, and so on. There are plenty of possible explanations, but none of them are completely convincing. Nevertheless, I'm looking for properties of the Earth that are rare and that are beneficial to life. In the Sun's unusually large mass, we seem to have found a property that's positively detrimental to life, as the Sun's resulting short lifetime restricts the time available for advanced life to evolve. So, having looked at the Sun's mass as being a possible peculiarity of the Earth that makes the Earth unusually suitable for life, I think we'd have to say that the case is not proven, because as far as we can see, if anything, it should make life less likely. So there's a problem with going down that route. Let's look at some of the other possible ways in which Earth might be unusual and particularly suitable for life. What about the large size of our moon? This certainly looks a little odd, as no other terrestrial planet in the solar system has anything more than a few small rocks orbiting it. But this doesn't prove anything, as it's a very small sample. There are only 4 terrestrial planets, Mercury, Venus, Earth and Mars, and even if large moons are common across the universe, it's not at all unlikely that we could be, by chance, in a planetary system where only one rocky world has a large moon. Furthermore, Mercury and Venus may have had moons when young that they have since lost. That's another topic I could spend an hour on. But instead, I want to say a few words about whether we need a large moon to have a stable axis. This is something that is frequently said, and it's certainly true that if our moon disappeared suddenly, Earth's axis would become unstable. But having a large moon that magically disappears after 4.5 billion years is not the same thing as never having a large moon in the first place. Billions of years of lunar tides have slowed Earth's rotation, and a faster spinning Earth has a stable axis even without a moon. It really is not clear whether possession of a moon stabilizes a planet's axis or, in fact, destabilizes it. So is Earth special because it has a large moon? Again, not proven. How about the existence of a large gas giant, Jupiter, that vacuums up rogue asteroids and comets and prevents them from hitting the Earth? This idea gained credibility in 1993 when comet Schumacher-Levy 9 collided with Jupiter and produced a truly spectacular impact and a temporary planet-sized scar. There's no doubt that such rogue impactors are far more likely to be swept up by Jupiter than they are to hit the Earth. And so it has been frequently claimed that Jupiter shields Earth from impacts. Unfortunately, there are a number of problems with this suggestion. For a start, it's not even clear whether low impact frequency is a good thing. The dinosaurs ruled the Earth for nearly 200 million years and only made room for us mammals after they were wiped out by an impact. Perhaps regular impacts are important to allow evolutionary innovations. Nobody really knows. And there's another, even bigger problem with the Jupiter as shield idea. The main reason why asteroids and comets go rogue in the first place is because their orbits have been disturbed by Jupiter. Jupiter is as much a cause of impacts as a shield against them. And in computer models of solar systems without a Jupiter, Earth actually suffers roughly the same number of impacts. So you can guess what's coming. As with the Sun and the Moon, the idea that the Earth is special because it has Jovian protection is at best unproven. So now I want to turn to properties of Earth herself. Is there anything about the makeup of our planet that seems particularly suitable for life, and perhaps something that could be rare in the wider universe? The most obvious first point to make is that our planet shouldn't be called Earth at all. It should be called ocean. And water certainly plays a massive role in Earth's habitability. There are good reasons to suppose this will be true of most life across the universe. That's another talk that could take the entire time I have. So for now, just take my word, please, that the water is important. The surprising thing is that terrestrial planets have any water at all. This picture shows the protoplanetary disk from which the planets condensed 4.5 billion years ago. As you'd expect, the disk is hot where it's close to the sun and much cooler further away. As a result, water can't condense into ice particles close to the sun. And so, as the young planets initially grow from the collecting together of small grains, the inner planets shouldn't initially grow with any water in them. The water we do have seems to have arrived a little later on, perhaps 10 million years or so later. At those later times, the solar system was an unstable place in which the giant planets were moving around, and as they did so, they deflected water-rich asteroids and comets into the inner solar system. But it seems that such instability is common in young planetary systems. And the implication of that is that water-rich inner planets should not be particularly rare after all. So Earth's copious water is yet another life-giving property for which we really have no good evidence that it's rare. Right, the next property I want to look at is plate tectonics. First, I should perhaps say something about what that is, and more importantly, why it matters. So this cartoon shows how plate tectonics operates on the modern Earth. Hot magma rises at the mid-ocean ridges where it cools and spreads out as a new tectonic plate. This results in plates that are slowly pushed away from the ridges by this new plate growth. And to make space for this, the plates eventually become cold and dense enough to sink back into the mantle at subduction zones. The continents ride piggyback style on these moving plates and occasionally collide to produce mountain ranges or split apart to form new rifts and eventually even new oceans. All this matters to life because it allows a constant exchange of materials between the Earth's surface, the ocean, the atmosphere, and the deep subsurface. Right? It's a two-way exchange. On planets, for example, without plate tectonics, you'd expect material from the inside to get to the outside through volcanoes, but there's no mechanism for getting materials back from the outside into the inside. But with subduction on Earth, there is a process that does that. And this two-way exchange ensures that important compounds, such as water and carbon dioxide, never become too concentrated or too depleted at the surface. Plate tectonics is an important component of the processes that keep our world in a dynamic balance that's quite unlike the extremes of absence and excess seen on other worlds. But does this make Earth special? That depends on whether or not plate tectonics is common on medium-sized rocky worlds. We don't see it on the other rocky planets of the solar system, but as we've already discussed, the sample size of 4 such worlds is far too small to draw any conclusions. So in an attempt to answer this question, planetary scientists have built computer models of how plate tectonics works. And then they've played with these models to see what happens when, for example, if you make a planet larger or warmer or wetter and so on. What does this do to plate tectonics? Does it turn plate tectonics on and off? What we're trying to do is to understand what are the requirements to have plate tectonics. And once we know what those requirements are, we can start to try and work out whether it's likely to be rare or common. Unfortunately, the current models contradict one another. Some models predict that larger planets will always have plate tectonics, whereas others predict that larger planets never have plate tectonics, and so on. At the moment, we simply do not know what properties allow plate tectonics to happen, let alone whether those properties are rare or common. So, whilst the evidence that plate tectonics is important for life is actually quite strong, we do not know whether plate tectonics is common or rare. And so it's yet another property of the Earth which is not necessarily special. How about magnetism? Does our planet's strong magnetic field make an oddball with unusual life-promoting properties? Well, this is certainly something that's frequently claimed. The idea is that our magnetic field deflects energetic particles from the sun towards our poles, where they generate aurora. And that by doing so, that protects the Earth's inhabitants from the particles and the Earth's atmosphere from being slowly evaporated off the Earth by the solar wind. It's certainly the case that an early Mars that was warm and wet lost its magnetic field billions of years ago, and that led to its losing much of its water and most of its atmosphere, so that it became the dry, cold world we see today. But on the other hand, Venus also has no magnetic field, but still retains a very dense atmosphere. It is, at the very least, a more complex story than often presented, and I'm afraid my conclusion, once again, is that it's not proven. So that finally brings me to what I think is Earth's most interesting life-enhancing property: climate stability. How on earth did the Earth manage to have 4 billion years of good weather? Not once in all that time did Earth's surface become so cold that water everywhere froze, although it did come close to that 600 million years ago. Not once did the surface become so warm that all the water evaporated. Though again, we've probably got quite close 3.5 or 4 billion years ago. But these disasters really did happen to Mars and to Venus, not to Earth. Billions of years of continuously clement climate is really surprising. Wet planets suitable for life are also worlds that have an inherently unstable temperature. When a wet world gets cold, it turns white with snow and ice. It then reflects sunlight into space and becomes colder still. In contrast, when a wet world warms, evaporation puts lots of water vapor into the atmosphere, and that's a powerful greenhouse gas. Quite simply, warm wet planets tend to become hot wet planets, and cool wet planets tend to become cold wet planets. Keeping a wet planet neither too hot nor too cold is a difficult trick to pull off continuously for billions of years. So did the Earth somehow become delicately poised at the right temperature and then stay put? Well, it's difficult to keep anything delicately poised, and in any case, billions of years of climate stability because nothing much changed is just not the correct picture. Earth's story is one of continuous change, not one of stasis. The most important change is that as our sun has aged, she's become brighter. and now emits 30% more heat than she did when young. The early Earth with its dim sun should have been 100 degrees colder than today, but she wasn't. One of the first people to point this out was Carl Sagan. If you're under the age of about 40, you may have no idea who Carl Sagan was, but he was the Brian Cox of the 1970s, an intelligent, articulate scientist who seemed to front up every science program on the telly. But Carl also wrote some high-impact scientific papers, and in one of these, he raised what he called the faint young sun paradox, the problem of why the young Earth was warm despite a much less luminous sun. The paradox actually has a simple solution. Either the early atmosphere contained more greenhouse gases, or the early Earth was less reflective, so that it absorbed more of the meagre solar rays. But as the sun grew older and warmer, the Earth's atmosphere and reflectivity must have kept changing to keep temperatures steady. Life played an important role in this. This picture shows you Royal Holloway, where I work. I didn't take the picture to show you the pretty building, though. Rather, what I want to show you is the green slime that I hope you can see on the wooden post. This stuff gets everywhere. You'll get it in a glass of water if you leave it for a week or two. And it's the same slime that grows on your windows and on your patio. And this cyanobacteria even grows under the surface of rocks in the desiccated, cold and otherwise uninhabited dry valleys of Antarctica. It's the single most successful organism on the planet. And when it first appeared, it changed the world. 2 billion years ago, when it first evolved, it sucked carbon dioxide from the atmosphere and spat out the lethally poisonous gas, oxygen. And oxygen also reacted with the methane that was in the atmosphere at that time, another strong greenhouse gas. So 2 billion years ago, the Earth suddenly got colder, but that compensated a little for the ever-warming sun. Then 600 million years ago, this organism evolved. Right, not the puffin. What I'm interested in is the yellow stuff that it's standing on, lichen. As it grows, this symbiotic combination of fungus and algae breaks up the rocks. And then the rocks react chemically with the atmosphere. And the enhanced chemical reactions remove yet more carbon dioxide. So 600 million years ago, when lichen first appeared, the Earth suddenly got colder. And again, that compensated for the ever-warming sun. The story doesn't finish there. 400 million years ago is when woody remains from the first land plants were buried in the earth to form peat, coal, and other plant-rich sediments. Now, wood is almost literally made from thin air. Carbon dioxide from the atmosphere is combined with water during photosynthesis to make the wood. So when wood and other plant matter is buried in large quantities, this removes carbon dioxide from the air. 400 million years ago, when land plants first evolved, the Earth got suddenly colder, and that compensated for the ever-warming sun. So as a result of biological evolution and also geological processes that I haven't really got the time to talk about, Earth has more or less kept a steady surface temperature throughout time. Somehow we find ourselves living on the best of all possible worlds. Everything that needed to happen to keep our world from overheating did happen, and at just the right time. How did we get so lucky? So some would suggest the Gaia Hypothesis. This says that the complex biosphere itself acted to impose good conditions. Life looks after life, and the biosphere adapts as needed to maintain or even improve the environment for life. I'm sure many of you have heard this idea and you may be quite attracted to it. But I'm sorry, I think it's sentimental tosh, lacking any supporting evidence. I prefer a different explanation. I think it's confused cause and effect. It's not that a complex biosphere gives environmental stability. Rather, it's that a stable environment is necessary to allow a complex biosphere to evolve. So there's an observer bias here. Any planet which doesn't have this climate stability doesn't give rise to intelligent observers like human beings. So intelligent observers, wherever they're found across the universe, will always find themselves living on a planet which, purely by chance, had a stable climate history. But that's just my opinion. Many of my colleagues will argue for Gaia as passionately as I argue for Goldilocks. If I'm wrong and Gaia is correct, then worlds with life will always have stable climates, and our world is not unusual. But if I'm right, the stability we've seen is not inevitable. Indeed, most planets where life has arisen will have died either because their worlds froze or because they overheated. That's a chilling vision of an uncaring and cruel universe. So a large part of me hopes that I'm wrong. And it's a controversy, so that leaves me with climate stability too, being an unproven special property of our planet. So is Earth special? There's certainly no single property of our world that I can point to that is indisputably essential for advanced life and indisputably very rare. But I've got one more trick up my sleeve. And that's to do with the fact that nothing lasts forever. And that includes planetary habitability. Mars, for example, was once warm and wet, but it lost its early clement climate billions of years ago. Earth too will not be habitable forever. So let's have a look at a few things that will terminate all life on our planet in the distant future. The first of these is the fact that our sun is continuing to warm. And eventually, even a highly reflective world with no greenhouse gas would become too hot for life. So when will Earth overheat? There are a large number of different estimates of this, but most of them suggest that Earth will become too hot for liquid water in 1 or 2 billion years' time. So the lifetime before overheating is 4.5 billion years till now, plus another couple of billion years, something like 6.5 billion years, the total lifetime over which a planet remains habitable, or at least an Earth-like planet, around a sun-like star. But that's not the only thing that might get us. A second problem is back to the axial instability I mentioned earlier. Today our axis is stable, but as the moon continues to slow our rotation, and as a consequence, as it recedes from the Earth itself, the stabilizing influence of our satellite will wane until in 2 or 3 billion years' time, Earth's axis will become unstable. Climate will then become wildly erratic, and complex life, at the very least, will become impossible. But do disasters come in threes? Here's a third ecological disaster for you to think about in our distant future. As the Earth slowly loses her internal heat to space, she's cooling down. And eventually the core will freeze into solid iron, and the mantle will become too stiff to flow. At that point, in about 4 billion years' time, we'll lose both the magnetic field and plate tectonics, and life will be doomed even if it's not succumbed to overheating or catastrophic climate instability. So there are at least 3 completely different ways that life can come to an end on Earth, and they are controlled by 3 completely different things. the time to overheating by the sun, for example, is controlled by the mass of the sun. The time to axial instability is controlled by the mass of the moon. And the time for cooling, so the time for plate tectonics and magnetism to shut down, is controlled by the mass of the Earth. So if these three things are independently controlled, they're not related to each other in any way, why are they all about the same size? Well, one way to answer that is that they're in fact all unusually long, by which I mean much longer than they would be on a typical planet. And that this unlikely combination of long lifetimes was a necessary precondition for the existence of intelligent observers, us. It's not that we somehow caused this to happen, but if intelligent observers can only ever appear on planets that have been habitable for a few billion years, then necessarily we must be living on a planet that has a lifetime that long. This is called anthropic selection. The Earth must have properties essential for our existence, even if those properties are extremely rare. Furthermore, if habitable lifetimes are usually short, then we can expect to be on a planet where all the lifetimes are only just long enough, because longer lifetimes are even less likely. Hence, they will all be about the same length, which is just a bit longer than it took for the observers to appear. This last argument is not what you call a sure thing. It perhaps suggests that our planet may be special in being habitable for an unusually long time, but there are, of course, other ways to explain the lifetimes coincidence. But the lifetimes coincidence is the best argument I've got. I've been trying to show for the last 20 years whether we live on a typical rocky world or upon one of the weirdest planets in the universe. And I still don't know the answer to that question. Perhaps it's time for a new generation of scientists to have a go. Thank you very much for listening.
Thank you very much, David. Can I ask members just to unmute and show our thanks? Interesting talk, very thought-provoking. Can we go over to questions?
Absolutely, yes.
Okay. Right. Yeah, great. Brilliant talk. Brilliant talk. Yeah.
Once I settled down a bit, I was a bit thrown at the beginning by my lateness, I'm afraid. But yeah, once I settled down, thank you.
There's probably other things that'll end us all tomorrow, but we'll not worry about them.
And humans, perhaps, but not all life on Earth.
Well, I agreed completely. Yeah. So Sean was first in with a question. Would you like to articulate your question, Sean?
Yes, thanks very much, Peter, and thank you, Dr. Waltham. That was absolutely fascinating. I was speculating on whether maybe your talk should have been called rather "Is Earth Special? Is Earth Early?" Because while all of the factors you've pointed out are so improbable to have come together to provide just the right planet for our kind of life, could it be the fact that although the universe is 13.7 billion years old, that if the universe is actually, as we understand, it's going to be around for another couple of 100 billion or trillion years, that it's simply ours is one of the first planets to reach all those lucky combination of events, and rather than being particularly special, it's just that maybe we're very early on from the universe's point of view of producing that kind of intelligent life, because even we humans 100,000 years ago weren't the intelligent observers we are today, and who knows what we'll be 100,000 years from now, and in cosmic time that's nothing, that's the blink of an eye. So I just wanted your thoughts on that, and I just wanted to make one very nice footnote to say thank you for using the nice Scottish legal term "not proven" rather than unproven, given you're speaking to the Astronomical Society of Edinburgh. If that was a deliberate touch, it was very well done.
Oh, that's an interesting point. It wasn't deliberate. I did actually grow up in Scotland, believe it or not, so maybe it's just a subconscious phrase. So, but that was many, many years ago. Yeah, on your point, people have attempted to discuss whether or not at what point in the universe's history planets could first have appeared, and so on. And my understanding of it is that whilst the very earliest populations of stars probably didn't have planets, in fact certainly couldn't have had because they only had hydrogen and helium, but pretty early on it did become possible. We don't really have the data yet to decide on that. I think it's a fascinating question. I would be surprised if we're the first, because I wouldn't expect us to be the first. The reason I say that, you may be surprised to hear myself call myself a good Copernican. Now, Copernicus, what he basically taught us, I think, is he taught us that we should try and think of ourselves as typical, as not being special. But on the other hand, I do think that the Earth is special. I do think that planets suitable for life are probably fairly rare. So the way I try to combine essentially the anthropic principle with the Copernican principle is by thinking that we're probably a typical inhabited planet, or at least a typical planet inhabited by advanced life. And that should be our starting point. And given that starting point, that obviously sets me up against thinking that there's anything special about us in the sense of being early. But all of that is philosophy and not data. It's not science. So you may well be right. Perhaps we're the first.
Okay, thank you for that question and the answer. That was excellent. Morris was asking a question about cyanobacteria. Morris, are you there? Maybe not.
So is it in the chat?
Yeah, it's okay.
Yeah, I found it in the chat. So how likely was it for the cyanobacteria, etc., to happen at the right time instead of the wrong times? Well, I mean, that is the, that's the $20 million question, isn't it? In my view, it was good luck, good fortune, and not good planning. But if it hadn't happened, we wouldn't be having this discussion. So that's the anthropic selection way of looking at it. But as I said before, there are a lot of people out there who, good scientists. I'm not talking about cranks. I'm talking about very good scientists who I have enormous respect for, who make very strong arguments in favour of Gaia. And the Gaia hypothesis basically says that the cyanobacteria is going to come along when it's needed.
Right. Okay, and then Stuart, you wanted to ask about the moon.
Yes, thank you. I thoroughly enjoyed your talk, as I did your book.
Thank you.
Is there another edition coming out of that, by the way?
Right.
Yeah, I'll let you answer that first. Then I'll
on the book. The book was what's politely called critically acclaimed, which means that it got very good reviews, and the few people who did read it seemed to really like it. But hardly anyone bought it, I'm afraid. So, in fact, it was rendered. It's not going to come out as another edition.
Yes, I noticed some rather cheap copies on the internet. I regret that I haven't bought one. I must remedy that, but I don't think it'll do you any financial favors.
No, I didn't retire to the Bahamas on the proceeds from it. Believe it or not, I've written one other book, which is a maths textbook, and I've made more money from that.
Well done.
Yeah. There you go.
My question is about the moon, but I have a supplementary question, which I'd like to put later. You were telling us that the moon is stabilizing the axis of the Earth, and yet in your book you say that large moons don't stabilize the axis of planets. Can you clarify that?
Yeah, it's, as I said, it depends on how you look at it. There was a classic paper in Nature about this about 1990 by Jacques Lascar, who is a very, very good astrophysicist, and he basically modeled very, very carefully what the Earth's axis would be like if we didn't have the moon. And he quite rightly showed that if we didn't have the moon and everything else was exactly the same, then the Earth's axis would indeed be very unstable. It would be changing its tilt by 50 or 60 degrees every few million years. it would be far too erratic to give us a stable climate. And that's all correct, and I've got no arguments with any of that. The problem is, as I said in the talk, it's essentially imagining that we have a moon for 4.5 billion years, which then suddenly disappears, which isn't the same as not having one in the first place. So I've done some much more simple-minded modeling than Jacques Lascar's, where I've essentially built Earth-Moon combinations by simulating the collision between Earth and Theia that's supposed to have happened. But I've done things like slightly different different angles of impact, whether it's head-on or glancing and so on, and produced lots of different moons of different sizes and lots of different spinning rates to the resulting Earth. And then I've modeled it forward for 4.5 billion years to see if the axis is stable. And the conclusion that I come to is that you're more likely to have an unstable axis if you have a large moon than if you have a small moon. But it depends. Sometimes you get lucky, sometimes you're not lucky. But generally speaking, having a big moon's a bad idea from that point of view anyway.
Thank you. My supplementary question is, are we alone?
No, again, because of this, we're a typical intelligent species. I think if there was only one form of intelligent life in the entire universe, that would be an extraordinary coincidence, because it would kind of imply that the probability was very close to 1 upon the number of planets or something, some such coincidence like that. So I don't believe that. I do think that there's a lot of other intelligent life around, probably some very advanced civilizations around. But I also think that the universe is so enormous that probably the nearest one is beyond the cosmic horizon and we'll never ever make contact with it. So the way I put it is that we're effectively alone, but I don't believe we are alone. No.
You mentioned that the universe might be infinite, but if it was infinite, then there would be an infinite number of Earths.
That's true. Yes, but we'd never make contact with any of them.
No, right.
Yeah.
Thank you very much.
Yeah.
Okay. Ian Smith has a very urgent question.
It was very interesting to hear about the events that have saved the Earth from overheating. So I'm just wondering what's going to save us this time.
Well, as in the present day.
Yes.
Yeah. Well, I think the problem has to find the solution. We are the problem, and we have to find the solution. It is that simple, and we can do it.
Okay.
Okay. Any more questions from the members? I think I've got the list done.
Yes, Peter, could I ask a question?
Yep.
Type it rather slowly. Thanks very much, Dr. Waltham, for your presentation. It was marvellous. Earth appears to be ideal for carbon-based life forms. What about other types of life forms? Do you think, given that there could be endless variations in planets and so on through an infinite universe, what about other types of life forms based on that are non-carbon?
Okay, yeah, that's another fascinating question, and like many questions in this general area, it's one for which we've got no data whatsoever, so everything is speculation. My personal view, and it is, as I say, completely speculative, is that again we are probably a typical form of life, so I would expect most forms of life to also be carbon-based. When I look at the properties of other possibilities, silicon, for example, is often mentioned. It just doesn't seem anything like it's good, as far as I can see. This really is getting philosophical, possibly even religious, but it seems to me like life is such an incredible miracle that for there to be in our universe 2 ways of making it would seem like an even bigger miracle to me. But I have got no data to base any of those opinions on at all.
Thank you.
Okay. Mark, do we have YouTube questions?
I do have one. I think you may have sort of answered this. Lorene asked, assuming Earth is special, Is it wise to consider that the same set of conditions as we have here could have happened in other galaxies, and hence intelligent observers like us might exist on other planets? So it's really, could our set of conditions exist elsewhere, and then might be people very similar to us?
I don't know about it. I guess it depends by what you mean by similar. As in that, they're not going to be bipedal, 6 foot tall, and blue eyes or whatever. I wouldn't have thought. But I do come back to what I said earlier. I think it's very unlikely that this has only happened once in the universe. It's far more likely to have happened a few times. I would have thought, purely from a statistical basis. But yeah, if it, the arguments are from convergent evolution that for example, eyeballs have appeared independently. I can't remember how many times it is, a dozen times or something independently, and various other similar arguments. People have come to the conclusion that life, if it does exist on other planets, is probably going to evolve in a similar direction. I have to say I'm not convinced by that argument. I think it's got some merits. I'm not saying it's wrong, but again, my gut feeling, based on no data whatsoever, is that the universe is likely to be far more interesting than that.
Yeah.
Okay, we have another one from Graham. Who asks, does what we know now equip us to terraform Mars or Venus for life, making them special too?
Ooh, right, yeah. I'm really worried about Mars, I have to say. My concern with Mars is that I think it's entirely possible that it's either got completely indigenous life, or that it's got life that's connected to Earth life in the sense that it either started on Mars and got transported to Earth, or vice versa, very early on in microbial form, and then developed. So the case for life for indigenous life on Mars, I actually think is fairly strong. I mean, and therefore I worry very much about even human beings setting foot on Mars, let alone going there and terraforming it. I think we need to protect Mars until we're absolutely sure that there's nothing there. If we, and it's very hard to prove a negative, of course. If we do become fairly sure that there's no life on Mars, and therefore it is ethically okay to start messing around with it, terraform is a fascinating idea. I can't see how you can possibly do it in much less than a few 100,000 years, though. So it's a very long-term project, I'd have to say. But yeah, it's a great thing to think about, great thing to talk about.
Stephen asks, would we recognize other life forms not based on carbon?
Well, again, a great question. How do you look for something when you don't know what it is you're looking for, kind of thing? It's actually one of the reasons, in lectures I give on these topics to our undergraduates. I talk about why are we looking for water-based and carbon-based life, and I go through all the various reasons why carbon and water seem to be particularly suitable. I go through my whole argument of we're more likely to be a typical life form than an atypical life form. But actually, the final argument I come up with is, how do you look for something that's completely alien, where you don't know what it is you're looking for? So I think some people have even suggested that there's a shadow biosphere on the Earth that we're completely unaware of. I don't know how to answer that question. I love it. It's a fantastic question. And it's the sort of thing I could spend hours sitting in a pub with a pint of beer talking about. But I have no data. I've got no. I don't know what I'd base any opinions I have on. I'm afraid, but it's a great idea.
Graham asked another question. What about non-rocky planets as possible homes for life, e.g. the icy outer system moons, possibly subsurface life, habitable oceans, though inhospitable on surfaces? Yeah.
So Enceladus and Europa, certainly very promising places for life in the solar system. And if we find life there, it's unlikely to be related to Earth. So that really would be an independent origin for life. And that would force us to conclude that life was common across the universe. The one that really fascinates me is Titan. because as I'm sure many of you are aware, Titan's atmosphere is full of hydrocarbons and all sorts of interesting organic chemistry at very low temperatures. And could life evolve under those conditions? But what really fascinates me is the strong likelihood that Titan is also probably an ocean moon. It probably has a subsurface ocean. So could Titan actually have two biospheres, two independent biospheres? I wish I could live for another 150 years and try and find out the answers to those questions.
Yeah.
I'll ask one last question from Erin. Global climate change and the ideal conditions Earth currently has to sustain life. So stop Earth being special, if it is special.
So, sorry, you're breaking up. I didn't quite catch that.
Sorry, Erin asked, could global climate change end the ideal conditions Earth currently has to sustain life? So stop Earth being special.
Okay, right. Yeah. Right, I'll give you the likely answer and then I'll give you the gloomy one. The most likely answer is from that point of view, we shouldn't worry. The Earth has been through major climate catastrophes before and it recovers. And the only reason that we need to worry about man-made climate change is that our experience of previous mass extinctions is that it took the planet 5 to 10 million years to recover. And that's not really much comfort to us or our great grandchildren, etc. So 5 million years is too long. That's the most likely answer. Is even if we do really make a mess of things and it wipes us out and possibly causes the equivalent of a mass extinction, the most likely outcome is that in 5 to 10 million years' time, the Earth will have recovered and it will be just as biodiverse as it was a couple of million years ago before we started messing around. Now the gloomy answer, and that comes back to if you might take it as an extreme form of anthropic selection. What if climate stability really is a difficult thing to do? And as I said, we're only seeing it because it was a necessary precondition for our existence. If that's correct, it's quite possible that the Earth actually has no inherent climate stability at all, and we're about to find out the hard way. But that's a very gloomy assessment. I don't actually believe that. But again, it's a discussion I've had with people down the pub over a few beers.
That's great, thank you.
Professor Waltham, that was absolutely fascinating. My advice, as always, is go and enjoy yourself while we can. Thank you very much. Can we all show our appreciation? Wonderful stuff. Really,
thank you. And apologies again for being a little bit late.
Oh, these things happen. Thank you very much.
Embarrassing when it does.
That was fine. Thank you very much indeed.
Okay.
If there's anything else, then we'll wrap up this evening, and thank everybody for attending. Thank you.
Okay.